Here's about the best we can say about eigenvalues and transformations. So we have a finite dimensional space, complex, transformation, taking that space to itself. Here's the key fact that we're not going to prove today. We'll probably prove that in a next video. There is a basis that'll make the matrix upper triangular. It's also tightly tied to eigenvalues. Upper triangular, of course, means 0 is below the main diagonal. Instead, let's look at the easier proposition that once we have an upper triangular matrix with respect to some basis, the diagonal entries are all eigenvalues. So upper triangular, we have the main diagonal. It's got numbers. Above the main diagonal, numbers. Below the main diagonal, zeros. And it goes all the way down. Finite dimensional, so there's n entries, complex. So if I'm looking at an eigenvalue, I'm looking at a matrix that has this on the diagonal, and everything else is unchanged. Lambda is an eigenvalue if t minus lambda I has a non-trivial null space. We want to show that that's the same as having a 0 on the diagonal. T is invertible is exactly the same as saying it's 1 to 1, and it's exactly the same as it's saying it's onto. And then for any transformation, 1 to 1 is the same thing as saying it has a trivial null space. Null space being the 0 element only. Alright, so now with these basic facts in our head, let's look at the claim. So my claim is that if the diagonal terms are non-zero, that characterizes invertibility. When we're saying it has an upper triangular matrix with respect to some basis, what we mean is this commutative diagram. So that E1 goes to V1, take it through that matrix, it's scaled, take it back up, it's lambda V1. Or just looking at the vectors themselves, if I take that vector through, it's lambda V1, take V2 through, it's then going to be lambda 2 V2 plus some number lambda V1, and so on. Key is that if you send an element through, that its output is in the span of all the preceding entries plus itself. This span property characterizes upper triangular matrices. So let's show that invertibility implies diagonal terms are non-zero. So this is the logic statement we're looking at, that all the diagonal entries are non-zero. It's going to be easier to show the contrapositive. If there is a 0 diagonal term, then t is not invertible. Remember, this is the contrapositive statement, which is equivalent to the statement. Not invertible, not 1 and 1. So for some j, lambda j is 0. tvj then is 0 plus a linear combination of all the preceding terms. We just saw that t of vj is in the span of v1 to vj, but that means the span of v1 to vj gets mapped to the span of v1 to vj minus 1. And since the v's are a basis, the dimension of the input is j, the dimension of the output is j minus 1, I lost a dimension. T is not 1-to-1, not invertible. To show the other direction, let's do it by showing that T is onto, which is the same as invertible for this special case. So T of V1, that's in the range. If I divide by lambda 1, any scale is also in the range, so V1 is in the range. Well, now we're just going to inducting our way through. Well, if it's good for U1, it's good for V2. T of V2, that's a range element. We just showed that V1 is a range element. So when I put them together and divide by lambda 2, it's still a range element. Any linear combination of things stays in the space. So V2 is an element of the range. You just continue this process. So for any j, you can do the exact same thing. A scale of Vj plus linear combination of the preceding elements, which are all range elements, throwing everything to the left-hand side except for Vj. Vj has got to be in the range. This is true for every j, so it's true for the whole basis. The whole basis is in the range, and T is on 2.